In this video, we'll be covering equilibrium problems where you have a very small value for your equilibrium constant, and then we'll be using what's called the assumption rule to solve the problem. So here's a problem: says Lexan is a plastic used to make compact disc eyeglass lenses and bulletproof glass. One of the compounds used to make Lexan is phosgene gas, an extremely poisonous gas. The initial pressure of COCl2 is 1 atmosphere. And the equilibrium constant is 6.8 times 10 to the negative ninth. So we're gonna set up like our ice table as usual, and let me show you I'll show you like the significance of this number. So initially, we have 1 atmosphere of this, and neither of these are present. So let's review real quick what K means. Remember that that K is equal to products, concentration of products, or in this problem, actually, it's the partial pressure of your products divided by the partial pressure of your reactants. Okay, so what is this number telling us then? So this is a decimal point and then 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then a 68 here. So at equilibrium, this number must be very, very small, and this number must be a lot bigger than this number. Okay, maybe it doesn't necessarily mean this is super small, but it means that compared these two, when you compare them, this must be way bigger than this, the reactants. So that's what this means. Okay, the partial pressure of your reactants or concentration of your reactants is way bigger when your equilibrium constant is that tiny, is way bigger than your partial pressure of your products or concentration of your products. So what that means is, since these are zeros, this must go down over time, and this has to go up by amount of x, and this goes up by x. So in our problem, this will be 1.0 minus x. This is going to be x, and this is going to be x. And what we do here is, since we know this to be true, and this is so tiny, we know that barely anything is going over this way. Why? Because this has to be true right here for this number to be so small. So what we do then is this problem is made a lot easier if we compare to the initial amount compared to 1.0. We just assume that we assume that x is pretty much nothing. Okay, but then we don't say that it's nothing because we're still interested in solving these amounts right here. We just say compared to this one, it must be hardly anything. Okay, but we are still, of course, interested in solving for x. So just relative to this number, we say that it's hardly anything. So let's go ahead and solve this problem. I'm gonna go. I have this set up on the next slide, and I'll set up my ice table. Okay, so this is 1.0. This is 0, 0, minus x. This goes up by x. This goes up by x. So 1.0 minus x, x, and x. Um, and let's see. Yeah. So now we set up our problem. So we have 6.8 times 10 to the negative ninth equals, so it's going to be the partial pressures of this times this at equilibrium. So it's going to be x squared over 1.0 minus x. And just take a look at how much easier this problem becomes if we just assume that we're going to assume that 1.0 minus x, we're going to assume that it's basically equal to 1.0. So then our expression becomes this: 6.8 times 10 to the negative ninth x squared over 1. Okay, so now all you have to do is take the square root of both sides, and then we'll get that x equals 8.2 times 10 to the negative fifth. So just as we assumed, because this is so small and equilibrium is the amount of this over the amount of this, we saw that since this is so small, that means hardly any of this goes that way. Hardly any of the reactant actually becomes X. And so this is actually what we solve for X. And so this is a very, very tiny number compared to 1. So this should be totally viable way to do this problem is using the assumption rule. In fact, almost all acid-base problems that we'll be encountering pretty soon will be using the assumption rule, and it just saves a ton of time. You don't need to plot anything to solve for x, to solve for the quadratic, so you don't have to do any of that stuff. And I'll show you the what's called the 5% check after we do this. So our final answer here, of course, was to solve for the equilibrium amounts. So so the partial pressure of CoCl2 at equilibrium is 1.0 minus 8.2 times 10 to the negative fifth, or basically it's still 1.0 atm. And then the partial pressure of CO at equilibrium is X, 8.25 times 10 to the negative fifth atmospheres. And the partial pressure of Cl2 is also 8.5 times 10 to the negative fifth atmospheres. Okay, so when is this valid? When can we do this? As we saw, it's just really, really helpful and make this problem a lot faster and easier. So when can you do this? I'll give you a couple pointers on the next slide. So we're gonna check to see if x is 5% or more of the initial amount. So if x is 5% or more than the initial amount, then our assumption that x was really, really small is will actually be invalid. So this is what we're going to do. We're going to divide the x value that we got from using the assumption rule by the initial concentration and then convert it to a percentage. So here's what we're going to get. So we're going to have 8.2. This is the amount that we got by using the assumption rule. Divided by this. So we're checking to see is x 5% of this or not. So this is our assumed. This is our x using the assumption rule. And then this right here was our initial amount because this is the amount we were comparing it to. We were just saying that x is too small to make a difference in this 1.0. So if we convert this to a percentage, then we get 0.0082, okay, which is way less than 5%. So the assumption rule is completely valid to use here. So here are a couple guidelines on when you can use it. So this is just from doing lots of equilibrium problems. I would say watch for this. So the reason this is possible are there's two reasons this is possible. It's because K was small, and our initial amount is big. Okay, or a partial pressure initial amount, partial pressure of a gas X initially. So this has to be really small, and this has to be, like sort of big. So here are some guidelines. Just watch for Ks that are um, smaller than 10 to the negative fourth. And so if your K value is around if K is around 10 to the negative second to 10 to the negative third or bigger, this may not work. Okay, so and if it equals these numbers, you're going to be like right on the cutoff line. It may or may not work. And you'll see with most weak acids, it's actually most weak acids are actually smaller than this, are 10 to the negative fourth or even smaller. So, and then with solubility, they're very tiny. So you'll have like stuff that's like 10 to the negative 38th equilibrium constants. So this is totally valid for those kind of problems. So watch for that, and then um, watch for initial amounts that are a lot less than 1 molar. So if your K value is around here and your initial amount is less than 1 molar, then you're probably not going to be able to use the assumption rule. So those are a couple guidelines. So here's a problem for you guys to try. It says when k's are small, so your turn. So as you see, this is way less than 10 to the negative 4. Okay, that remember that was kind of like my guideline. And then it looks like our concentration is going to be about zero point 0.1 molar. And I know that's less than 1, but this is so tiny that this is not even going to this won't even matter. Okay, when your K is that small. So go ahead and give this problem a shot, and let's see how you guys do. That's the end of our tutorial.